A light, rigid rod with masses attached to its ends is pivoted about a horizontal axis as shown. When released from rest in a horizontal orientation, the rod begins to rotate with angular acceleration of magnitude. So to find the angular acceleration of this system, you'd have to use that the net torque equals the moment of inertia times its angular acceleration. So T net equals, the first thing you would do is notice that from the pivot point, each mass has its separate length, and there's a force of gravity pointing down on both ends. Since it's at rest, the normal force would be equivalent to its gravitational force. So when you're solving for I, you're doing the moment of inertia of both particles, masses, you could say. So I equals the mass times the radius squared. So for this side, the mass is 3m times the length is L squared plus m times 2L squared times the angular acceleration equals T net. And you combine, you get 4m L squared plus 3. I went that way. I don't know why. To give you a net torque of 7 squared times angular acceleration equals the net torque. And then after finding what the net torque equals, you can say that you should know that the force perpendicular times the radius is equal to the torque. So you would find the torque of each mass on both ends to equal the net torque. So the force that's perpendicular to the radius is the normal force, which is equal to mg. So 3 mg times its radius L plus just mg times its radius you're not gonna add it because it's the difference, the force. To find the net, it's the total force since they're in opposition. Yeah, so it's gonna equal 7 squared times angular acceleration. Then you're going to divide for this would turn out to be just mgl for 7ml squared. You can cancel out the m, and 1l would equal this, so g over 7 equals the angular acceleration. In this problem, there was a uniform stick that has the length L, and there's a mass on one end of the stick, and the moment of inertia about the center is I, and they want to know what the moment of inertia is of the combined system about the center of the stick. So to approach this problem, you would have to know that the moment of inertia equals I times the mass times the radius squared. Since they want to know it about the center of the stick, you would have to, the radius would be half of the length. So when you start plugging it in the formula, you would use what the moment of inertia that they gave you before, because it's combined in the system. So I equals I naught plus the mass times 1/2 the length squared. And then when you have to like distribute the squared to both the 1/2 and the L, so then you'd get I plus the mass times 1/2 times 1/2 times L squared. And then your final answer would be I plus 1/4 the mass times the length squared. In which of the following diagrams is the torque of about point O equal in magnitude to the torque about point X in the diagram above? All forces lie in the plane of the paper. So to answer this question, you would first have to find the torque of this diagram. And since they want to know the torque about point X, the radius would be L. And finding the torque, it's the force perpendicular to the radius times the radius. So they indicated this force here times the length. So the torque of the diagram is FL. And then going through each of the diagrams, if you were to find the torque of this one, there is no force that's perpendicular to the radius, so this would just have a 0 torque. And for this one, the force perpendicular, there's a force perpendicular, but the radius is half of what this is. So the torque here would be F times L over 2, and that's not equal to this one's torque. And then in choice C, to find the force perpendicular, you would have to use trigonometry to find the force on the y-axis. So I did that 2 cos of sine times the length would equal the torque. So the cosine of 60 is 1/2 times 2 gives you 1. So that is the force times the length. So the torque of this equals FL, which is the same as that. You just had to find the torque of each diagram. A turntable that is initially at rest is set in motion with a constant angular acceleration. What is the angular velocity of the turntable after it has made its one complete revolution? So let's do this. So some givens that you could determine already is that the initial velocity, angular velocity, is 0 since it's initially at rest. And they want to find what the final velocity is. And since it said it made one complete revolution, we assume that this is a circle, so the theta will equal 2 pi. And then from there, you have to determine which kinematic formula you would use to solve for the angular velocity. So I chose to use that the final velocity, angular velocity squared, equals the initial squared plus 2 times the angular acceleration times the angular displacement. So this would equal 0 squared plus 2 pi. That's gone. And then you would have 4 pi times the angular acceleration equals the final angular acceleration squared. Then you'd have to take the square root. And your final answer is the square root of 4 pi times the angular acceleration